Thank you all for joining us tonight. So this is the second talk for the IGCP648 virtual seminar. So I'm Luc Doucet, your host tonight, and tonight we have Dr. Richard Palin. He's an associate professor at Oxford, and today we'll present Mafic Archean continental crust prohibited exhumation of orogenic UHP eclogite. So Richard, the audience is all yours.
Great. Yeah, thank you. Thanks for the invitation to talk about this. It's something we've been working on for, I'd say, over 2 years. It's recently been published, and I'll fix this up on the second page. Let me go forwards now. So this is a really well-timed talk, so I'm pleased. This paper came out just 2 days ago. So it's a Geoscience Frontiers, open access. You can download it. I just did the proofs this morning, so my cat has decided to sit on me now. And I'm going to go through in this talk like the kind of thought process that we had to get to this point. And it might be controversial, as some of my past studies have been, some of my future studies surely will be. But I'll try and outline the limitations, the caveats, and the importance and conclusions, and then you can make your own decisions. And I'm very, very happy to get feedback. So yeah, this is the author list. It wasn't just my work, a lot of different contributions by different people who've all helped to get this in final form. So there's one main question that this work and other pieces of work coming from my research group have tried to address either directly or indirectly over the past 5, 6, 7 years, how long it's been. And that is, when did plate tectonics start on Earth? And it's worth, of course, discriminating between plate tectonics and subduction, because they're not one and the same thing. You certainly need subduction for plate tectonics, but the opposite is not necessarily true. You could have isolated subduction complexes in a global scenario that is mostly stagnant lid, where the plates are not moving horizontally. This is not the point of this talk. Obviously, you can read up review papers or primary research papers on this topic. But I've put in this timeline here to highlight the background to this main research question. So on the left, we have a very, very short list of exemplars for the studies that have estimated or reported when plate tectonics began on Earth. These will range from very recently in Earth history, Neo-Proterozoic, Hamilton, Stern, for example. Some of them go way back in time. Hopkins, Mark Harrison's group, his collaborators, would suggest that plate tectonics has operated since the Hadean, and a lot of other people will have dates in between, centered around the Meso-Archean. I think this is, most people come out with numbers that are close to 3.2, 3.1, 3 billion years. Now there's some lines on there's some points on the right-hand side, and there's some hours I've highlighted. These are key events in Earth history that would help us to answer this kind of question. The reds relate to supercontinents, which I'm not going to talk about now, but are of interest. The blues are more petrological, and there's some lines here that are highlighted specifically. The oldest unequivocal UHP eclogite is 0.62 GA. Whereas the oldest unequivocal HP eclogite, so high pressure quartz bearing, is at around 2.1, 2.15. This is Meso-Proterozoic. And if we assume that plate tectonics has operated for some period of time longer than 2.1 billion years, as shown by a lot of these estimates that center around somewhere in the Archean. If we assume, for example, that I am correct in my 2020 paper, which is a good assumption, I would argue, from my point of view. So we have a 2.9 GA onset of plate tectonics. Well, where are the eclogites in this intermediate time period? There's a gap of 700 million years between that point in time and the oldest HP eclogite, and there's an even longer gap in time for UHP eclogites. And there must be a reason for this. And of course, you could argue that they formed and they were exhumed and they were all overprinted, so there's no evidence of them left. That's a valid argument, which you can never really, I suppose, completely dismiss. But there may be other reasons, and we're going to explore one of these possible reasons here in this talk. So why is constraining the age of plate tectonic onset a problem? Well, to do so, you need to identify particular characteristics that belong to the plates. So you'd need to either prove subduction and or independent plate motion or rotation. This could be done with paleo-mag, for example. There's a paper by Brenner in 2020 that has done this for some Australian rocks. pushed one of these ages back into the Middle Archean, I think. The bottom line is that many of these lines of evidence conflict. And in our 2020 Earth Science Review paper, we kind of divided these lines of evidence up into four. The first one would be geodynamic or numerical modeling. Not so much evidence, but model results that might help you understand when plates were coherent enough to subduct, what happens to mantle potential temperature and plate strength. That could be one line of evidence that you could draw on. There's stuff like isotopes and trace elements that you could use to identify when crustal materials were started to be transported from the surface into the interior. This doesn't have to be by subduction, but you could argue for subduction in particular cases. Styles of deformation and magnetism, so tectonic arguments. You might look at when there's a dominant change from dome and keel architectures to more linear arcs and maybe large-scale strike subfaults, horizontal motion of plates. And the fourth type of evidence that we highlighted was key rock types, petrological evidence, in particular blue schists, which are well known by everybody on this call to be diagnostic indicators of subduction, and HP, UHP eclogite. Eclogite itself is not a diagnostic indicator of subduction, because if you thicken the continental crust enough, its base will eclogitize. And we see that in the Himalaya today, in the Pan extremely thick crust with an eclogitized root. So my cat is in the screen here. So we've done the blue schist problem. We've solved that in inverted commas in 2016. So now I'm going to focus on the HP, UHP eclogite. And I assume everybody here knows, but if you don't, the difference between those two is whether your peak pressure reached quartz stability field or coesite stability field. And there's a transition line, this polymorph transition line in PT space that has positive slope, and it occurs at about 2.6, 2.7 gigapascals at around 500 to 900 degrees centigrade. So if your peak metamorphism is below the line, you're HP, and if you're above the line, you're UHP. So this is a plot of apparent peak metamorphic gradient. So yeah, the y-axis is on the side, sorry. 3 times. This is a plot of all blue schist and eclogites in the geological record. This is obviously data taken from the Brown and Johnson dataset. I've modified it in some way and explained the modifications in the 2020 Earth Science Review paper. And I've color-coded it here. It's a bubble plot. I quite like this kind of style of plot. It's a bubble plot showing peak pressure reached, so you can see the kind of magnitude at first glance. And we also divide HP into UHP with these colors. Now there's one significant outlier on this plot, which is what I've called here a faux eclogite from Greenland. And this is from the Glassley et al. Paper 2014. I'm not going to talk about this. It's actually a very strange work. It's a complete outlier in terms of this plot. It supposedly reached extremely high pressure, 7 GPa. I said I wouldn't talk about it, and here I'm talking about it. I'm going to ignore it for now because it is a significant outlier. So we'll just cross it off. And from what I've read and from what I've heard of other people, it's not really an eclogite in the same sense as the rest of the rocks that are shown on this plot. So we will leave that for now. But this emphasizes what was said before. The oldest UHP rocks with peak pressures above this 2.7, 2.8 GPa cutoff are about 0.6. But if subduction has been occurring since at least 3 billion years, well, where's the rest of them? So secular change in metamorphism, there's been changes in Earth systems through time. Cooling of the mantle is one of the major changes that we have not observed. We can't observe that, but we can look at the rocks and we can infer the mantle has cooled down over time. The Hertzberg et al. 2010 paper in EPSL is the key reference here. And it shows that mantle potential temperatures decreased by about 50 to 100 degrees C per billion years. Now for oceanic crust, this has significant consequences. Hotter mantle makes a more mafic crust. When you partially melt the mantle, you have a larger volume of mantle melting and it has a higher magnesium content. And we showed in 2016 in this Nature Geoscience paper that affects the stability of glaucophane to form in crust. And that would help to explain, it might not be the only reason, but it would help to explain the absence of blue schists before this time. Now that's oceanic crust. What about the continental crust, which you might also expect to have had secular change in composition, architecture, everything else, due to these other changes in parameters like mantle potential temperature or anything else that's happening in the Earth through time. So what we would want to know is we would want to know the bulk composition, the petrology, the architecture, the thickness, anything interesting about the continental crust as a function of time. Now, working out bulk CC, continental crust composition here, for Precambrian terrains is obviously very hard. It's quite difficult for modern day terrains, Paleozoic terrains. But the problem with going back in time is you've had the chance for these rocks to be eroded. You may have lost a lot of the upper surface of the crust through erosion. The crust could have been reworked. It's been around longer, so it has more chance to be remetamorphosed and deformed. There's also less exposure because the amount of rocks that we have of a particular age is inversely proportional to that age. There's less old rocks than there are young rocks. It's just an obvious statement. Now, some people, Ken Condy, for example, have produced some quite reliable major element trends in the continental crust over time, or the upper continental crust, I should say, the UCC. There's been an increase in titanium, a decrease in magnesium, and a change in the potassium to sodium ratio over time. And these have been attributed to decrease in the proportion of komatiite, these very high magnesium basalts that you find on the top of mantle plumes, and also general high magnesium basalts that would form as a result of the hotter mantle potential temperature. These have decreased in that proportion through time, and the sodium to potassium ratio of granitoids, TTG-like magmas, has changed over time as well, which gives you this change in the potassium-sodium ratio. That's major elements. The minor elements can be just as informative. They can give you a separate perspective, but this is where you start to get a divergence in interpretation about what these trends mean. So there was one paper put out in 2016 in Science by Tang et al. And they used nickel cobalt and chromium zinc ratios to work out proportions of these three key rock types, these ultramafic, mafic, and, well, felsic, I guess, for granites, but TTG-like rocks in the Archean. So in the late Archean, I don't know if you can see my cursor or not, but it's on the far left, they have a high proportion of granite, a certain amount of basalt and komatiite. In the early Archean, there's a bit of a switch, and they say that the very old continents, this is continental crust we're talking about, or at least the upper portion of the continental crust, was dominated by basalt. 40 to 80 is a bit of a range, but the sentiment is still there that you have a more mafic continental crust. Then Greber comes out with a paper in 2017, just 1 year later, looking at titanium isotopes, and comes up with the opposite interpretation. He says that the crust has been dominantly felsic through all geological time. So this is but two examples of these competing interpretations based on trace elements and different isotopes. So we're already starting to see different end members forming. You might invoke other evidence for a more mafic Archean crust. There's a paper by Behem et al. 2015 in Geoscience, where they do some inverse modeling of rubidium-strontium and strontium-strontium ratios to work out the general composition or the general petrology of source rocks that were eroded to give you volcanic rocks in the geological record. I would just direct you to this paper to read more about this, but the curve that I'm showing here from the paper gives the general idea that the continental crust, the uppermost surface of it, was more mafic before 3GA and then has become more felsic, more differentiated over time. Bolhar et al. 2005 GCA put out a sedimentological study of quite immature clastic sediments from the Isua complex, and the compositions of those sediments and the mineralogy of those sediments implies, again, that you had a very mafic source region. Now, of course, these sediments are just sampling the upper surface of the continental crust, but we'll get onto in a second why the UCC is actually one of the regions that you would want to focus on for this kind of work. So there is a divergence, like in everything in geology. There is no acceptance about what the Archean crust was looking like. But what you do have is you do have suggestions that it may have been more mafic than previously thought. And this is what I want to emphasize. I actually don't sit in either one of these. I don't take one of these sides, but I'm quite interested and happy to say, well, you know, what if some of these proponents for a more mafic crust are correct? You know, what are the implications of that end member? So whether or not you believe that, you should at least acknowledge that this is a testable hypothesis. We can have a look and see what would happen if it were true. So debate rages on, but are there key implications of having a more mafic Archean crust? And obviously the short answer is yes, there are significant implications. This is a simple task diagram plotting up some of the historical data from Condi, 1993, the Greber data that I mentioned, and a very recent paper by Chen et al. In GCA, which is where I've taken a lot of this information from that we've used as a basis for the modeling. You can see that the Chen data stretches all the way across the task diagram, the Archean crystal compositions, basalt to basaltic andesite. And there's a big jump between 3GA for Mesoarchean, and 2.4 for Proterozoic. This is what their data show. So this is what we can work with. So the key question to answer, or to ask and then answer, is, if exhumation of Phanerozoic eclogites is significantly assisted by them being mafic bodies encased in low-density felsic crust, what would happen in the Archean if you had an encasing crust that was less felsic than today? That's the key question. So we whipped up these nice sections. Of course, these are based on the classic sections by Hawkesworth and Haywood. Just put my own color scheme on, really. But it's a way of demonstrating the changing proportions that Chen et al. Have put forward for these rock types through time. So the Archean crust is relatively mafic, it's relatively thin, and it's certainly less differentiated than you would find in Phanerozoic crust. Proterozoic and Phanerozoic crusts thicken up. And here, this is another way of showing how we're discriminating UCC from LCC and MCC. So going by Rudnick and Gall's definitions, upper continental crust would just be the top third. So for a 36-kilometer crust, it would be the top 12 kilometers. Or for an 18-kilometer thick crust, it would be the top 6 kilometers. This is a figure taken directly from the paper. So now onto the many caveats that will head off some questions at the end, hopefully. So caveat one, not all eclogites are orogenic. And we stuck orogenic in this paper title for good reason. Many different types of eclogites. And I've even mentioned that you don't even need subduction to form some of them. They can form the mafic roots of continents that have thickened considerably. Some eclogites occur as xenoliths and mantle-derived magmas, but they're proportionally very minor in the geological record. And we're not trying to, if you're going to try and put out one of these ideas that is applicable to many different terrains, you would want to focus on something that's volumetrically important, and this is not the case for these xenoliths. It's kind of also the case for blocks in tectonic melange. These are evidence of subduction, but these are just blocks that are entrained in these melanges, these accretionary prism materials. And it's hard to model their tectonic evolution. And there's other eclogites that you find in the geological record that are literally exhumed pieces of oceanic lithosphere. I think some of the alpine eclogites of this type. I've never worked on anything alpine, so I can't be quite sure, but I think Monviso is one of these examples. Now, they are exhumed by extensive serpentinization of the lithospheric mantle portion of the oceanic lithosphere, and that provides the buoyancy to get them back to the surface. They have no bearing, or they do not depend whatsoever on this supposed change in composition in continental crust composition. So for now, we can ignore them. It's not a type of orogenic eclogite that we want to focus on. And secular change in oceanic crust composition has been dealt with in different studies. So another big caveat, which is no doubt going to cause a lot of people some discomfort, is that we're using measurements of upper continental crust, and we're saying, well, let's treat this as sympathetic continental crust. And, this is hard to defend. And one counterpoint to this would be that Archean continents were likely much less differentiated, more poorly differentiated, because of the absence of plate tectonics. And the Duhem figure from earlier made this point. If I can just flip back to it, differentiation increases as plate tectonics kicks in, and that's when you start getting this change in the composition of the upper continental crust composition itself. So a pre-3GA crust might be more homogeneous than you would initially expect. So UCC being applied to depth, is something you can work with. Another point to argue why this is fairly defensible is that if you look at analog and geodynamic or numerical models of subduction, you actually see that the UCC, the upper continental crust, and or the MCC will preferentially weaken and detach from the lower continental crust during subduction. We see this in the Himalaya today. India moving forwards towards Asia, the lower crust has continued to move forwards throughout the whole of the collisional history. But it was the upper crust and some parts of the middle continental crust that were actually involved in the upper crustal deformation. So there's detachment between the two regions. So if you don't find a way to actually separate out the upper continental crust and lower continental crust, if they're fused together and cannot detach, then it doesn't really matter what the compositional change in the UCC is, because it's never going to be exhumed anyway. It's going to be carried down the subduction zone and end up in the base of the mantle. So for now, I mean, people might not like it, but we're just going to say that the UCC compositions reported by Chen are applicable to the crust itself. So I also know that some people on this call might not be familiar with the techniques that we're using. So here's like a 1-minute introduction to them. So we did petrological modeling, which is the tool that I use consistently for my work. This uses phase diagrams, which are themselves graphical representations of the equilibrium state of a system as a function of physical or chemical, intensive or extensive variables. It's not a very concise definition, but it's a good one. One example here would be H2O for water, ice, steam, for example. Like we know that if you heat water up, it's going to boil, and if you cool it down, it's going to freeze. And we know the properties of each of these phases, ice, water, and steam, and we can draw a phase diagram to show their relative stabilities as a function of pressure temperature conditions. The same thing, we can do the same thing for rocks. Water is compositionally simple, rocks are compositionally complex, but the same rules apply. And we can make phase diagrams and map out the stability of different phases, minerals, /melt, /fluids, as functions of P and T. And this is what we've done here. They're extremely versatile. You can do forward and inverse modeling. And the modeling shown here is obviously a forward type of model. You know, we don't have an answer. We're seeing what would happen if we set up a problem in a certain way and let it run. So here is the model setup. So these are all data from Chen et al. 2020, the GCA paper, buried in the supplementary information, but it's easy to find. So in their table, they use their copper concentrations that they've measured in these shales and diamectites to do an inverse model to produce lithological proportions for upper continental crust through time. And I've highlighted the rows of importance here from that table. So in the Meso-Archean at around 3 GA, they have a variation themselves. There's uncertainty on their numbers. And they have Komatiite varying from 0 to 36%. Basalt varying from 75 to 64. Felsic rocks varying from 25 to 0 as well. So we actually chose the middle of these 5, thinking that there's going to be, a kind of arithmetic mean of this range anyway. But we do some sensitivity testing later, which I'll get onto, just to try and encompass this entire lithological range itself. Obviously, I can't defend or even outline much of how they've reached these numbers. But as I said, I was quite happy to use the numbers to test this hypothesis. Now, another part of the model setup is explaining how we treated subduction zones. So the working model is actually you have this continental margin, and you have a mafic dike or sill intruded into it. And this would be exactly the case for the Himalayan type eclogites, which are kind of the archetypal orogenic eclogites. You have felsic continental crust intruded by mafic dikes, and then during the very early stages of the India-Asia collision, the continental margin is dragged down the subduction zone, kind of telescoped and thinned, and some parts are returned to the surface. And then the whole terrain, of course, is the crust plus the intrusions itself. So we did some modeling to work out the metamorphic phase transformations in the host rock, whether it's felsic, intermediate, or mafic, and in the dikes themselves, which we're treating as the potential bodies that could be eclogitized. And this harks back to that field photo I had on the front page. You have these felsic hosts and these mafic pods and lenses. Now, we did modeling in a fairly full system to make it as geologically realistic as possible. We had 2 end-member states for hydration, nominally anhydrous and minimally hydrated. And this is a way of saying water, or H2O, in these systems is a mobile component, and it can enter or leave the system almost as it pleases. And that's kind of awkward because we need a fixable composition to do this modeling. So we did 2 end members for hydration state and said that you could have these end members or anything in between. Minimal hydration here means that you just have enough water to allow metamorphic reactions to occur, but you're not flushed with water, so you haven't got too much water. So there's no kinetic limitations on equilibrium. It's one of the major points. So the subduction zone geotherm, which no doubt will be a sticking point for some people. We used the average one of Penniston-Dorland et al. 2015 in EPSL. And this was an improvement, so to speak, on an earlier subduction zone proposed by Syracuse et al. In PEPI. Sarah Penniston-Dorland, she traced a subduction zone geotherm that actually goes to PPT conditions for natural eclogites, which one might imagine would be more reliable than having a forward model of subduction zone geotherm itself. Importantly for this point, the PT conditions that Sarah has put forward encompass Phanerozoic and Proterozoic eclogite PT conditions. So it's actually suitable for all the rocks that we have in the geological record, because we don't have Archean eclogites to test against. So last point here, hot subduction. Caveat 3, some like it hot. Subduction zones in the Archean, we don't know. So Jeroen's paper is splashed up here. There's actually a really great summary. It's in our reps, 2012, I think, but it could be wrong. He goes into a lot of detail about if subduction could occur, and if it did occur, what would it look like. Very good work, but I think the joy might still be out. Did subduction occur? And if so, what would be the temperatures on the slab surface? Now, I have put my own paper up here again, just because I can. In the appendix for our next Geoscience paper, we had a lot of discussion about, how do we choose PT conditions to model for Archean subduction? And we cited a paper by Kirby, 91 in Science, where he says that, first order controls on the slab surface temperature are essentially just convergence rate and slab age. Things like changing mantle TP, slab day angle, they have less influence. So then you can go and look at review papers by Coronaga, for example, who have calculated or inferred changes in plate velocity through time, for example. The bottom line here is that with these different sources of information, we've tied them all together. And the arguments are that even a hot Archean slab surface will resemble this average subduction zone that Penniston-Dorland uses, because she will be considering flat subduction that occurs on the modern day Earth, for example, flat slab beneath the Andes. This is incorporated within this larger data set. And there's no reason to suggest that Archean slab surfaces were significantly hotter than hot Phanerozoic subduction surfaces. This is another one of the caveats. Feel free to argue with it if you like. Okay, so finally, some results. You've been waiting for the results, I'm sure. Too much introduction. So what we did is we had these different rock types. So UCC here is uppercontinental crust. We've got 3 GA for the Archean example, 2.4 GA for the Proterozoic example. We also did Phanerozoic as a test, but there's no real need to do Phanerozoic because we know we have eclogites that have been exhumed. So I'll focus on these 2 time periods just for the sake of argument. These are so-called mode box plots that we like to do for petrological models, and they show changes in mineralogy, volume percents, along PT paths. So the x-axes, there's 2 axes. One is pressure, one is temperature, and the vertical axis is volume. And it's a good graphical representation of the change in mineralogy. So if you look at which minerals form and what rock types that you have forming, in the upper continental crust, the old Mafic Archean crust, looks pretty much like an eclogite itself. And that's perhaps unsurprising because the bulk composition of the calculated crust by Chen is basaltic, essentially. The UCC is less Mafic and the Proterozoic, and it looks more like an orthogneiss. Here's the key diagram to look at. This is the change in density for the individual components and the individual terrains of the different ages. So the green line here is pyrrolite, which we just use as background mantle. Doesn't matter if you use Lertzlite, Hartwigite, pyrrolite. The density is actually very similar. So the red lines are the intrusive basalts, the bodies that have gone into the continental crust. And then the blue lines are different ages of the upper continental crust itself. And as we said, if you have a more mafic continental crust in the Archean, it looks pretty much like a basalt itself. So its density tracks up significantly. And it will reach this point of no return, so to speak, where it becomes negatively buoyant at around 2.3 GA in a minimally hydrated scenario. So the whole point here, the crucial point to note is that these mafic continents become more dense in the surrounding mantle before you cross the HP-UHP transition. So you can't return them without external forcing. They can't return to the surface of their own volition due to buoyancy. So you will never be able to return. You will never be able to make a UHP eclogite and return to the surface by buoyancy alone, unless you have some other force that's involved, like it gets caught up in a mantle diapir and brought to the surface. On the left, oh, sorry, that was the left. On the right, my mistake. These are bulk terrain densities. So we have the individual components on the left. And if we went to the Himalayas and we saw what proportion of dikes you have inside these felsic gneisses, 10% is extremely generous, extremely generous. Like volumetrically, these dikes probably make up less than 1% of the entire terrain volume. But we said, you know, let's be generous and let's see what happens when we increase or decrease the amount of host rock that you have. It doesn't matter whether you have 90 volume percent, 99, 99.9. The composite terrain density kind of tracks along with the composition of the crust itself. And the old Archean crust, if we assume it is more mafic than today, reaches this point of no return, this transition in buoyancy at around 75 kilometers, which is before you reach the quartz coesite transition. So I mentioned that we did sensitivity testing. This is based on the fact that Chen et al. Has variation in their lithological proportions. This is just a graphical representation of the Monte Carlo procedure that we use. There's some points scattered around the test diagram to show all the different simulations that we did. Here's the outcome of that sensitivity testing. There's box and whisker diagrams tracking variations in density at different PT points along the supposed PT path. And the majority, so 73%, 89%, 92% of these randomized compositions show a similar profile to this mean composition that we used. So of course, someone could be argumentative and say, oh, well, there's 8 of your results for this example here that did not attain negative buoyancy. And that's true. So who knows, in the future, we might find an example of an Archean crust that has been subducted to UHP conditions and brought back to the surface. But I can tell you now that these 8% will no doubt be the extremely felsic and members of the randomized bulk composition cloud. So it all depends which way you look at the data. This is M high and NaN, so minimally hydrated, normally anhydrous. The detail of this is in the paper. I don't think it's worth spending much time on the results themselves. The implications, and I'm conscious of the time, Luke, I'm not going to run over, don't worry. The implications are short and sweet, actually. So we've talked about these hot subduction zones. Some people might not like the idea that you actually have subduction at all, and that you might think that that obviates the entire results of the study. So in some cases, you might have lower crust dripping away into the mantle or delaminating away, and you might look at what happens to those drips. Do they eclogitize? Can they be brought back to the surface? Could they be UHP eclogites as well that are brought back on the head of mantle plumes? And it turns out it doesn't really matter whether you're looking at cold subduction, hot subduction, or dripping away, because the positive slope, the positive dp dt slope for the quartz coesite transition means if you have a hotter subduction zone geotherm, it makes it even harder to achieve UHP conditions because you have to go down even deeper because you have this positive relationship between pressure and temperature. And by that point, you have certainly eclogitized. So the quartz coesite transition has a positive slope itself, and the mineralogical transitions that give you eclogites that form garnet plus anthracite have a similarly positive slope, but it's much shallower. So you will always form an eclogite that becomes denser in the surrounding mantle before you reach UHP conditions. What you need is a low density felsic crust to bring you back to the surface. So whether it's a drip, shallow, steep subduction, it doesn't really matter. The porosity of felsic material in the lower crust preclude this as being a mechanism as well. There are some interesting implications that don't relate to subduction per se, and these I'm less confident about because this wasn't my area of paper, but I'm not a geophysicist. But I did get one of my geophysics friends who's very good at this stuff, very, very good, and he worked out some lithospheric strength envelopes, assuming that you had a more mafic Archean crustal composition. And I can explain these fairly well, I just don't know the procedures he used in generating them. So if you look at the LSEs for an Archean mafic consonance versus a felsic modern day consonance, then you have a difference in whether you have a weak zone or not. So if you have a Mafic constant, you're kind of contiguous in strength. In the geodynamics community, they call this creme brulee. Whereas if you have a weak lower crust, you have a jelly sandwich type model, where you have this weak horizon in between two strong horizons. That's where the jelly sandwich analogy comes from. Now, this has implications of whether or not you can peel or drip away the lower crust. We'll get onto them on the next slide. But there's one more point to note for these simulations of the early Earth. If you use, many people have assumed that you have felsic crust, felsic continents in the Archean, and therefore they would use particular flow laws, wet quartzite flow laws. And this is fine if you had felsic crust, but if you're actually more mafic, then a wet quartzite flow law is not appropriate. You would want to use something like diabase, which is the US term for dolomite or basalt, basically. So maybe it calls into question some of this past modeling that's been done, assuming felsic continents. Of course, there are TTGs in felsic continents, in Archean continents. No one's arguing that. But it's whether or not you have a dominance of basalt over TTG or komatiite instead, which some of these trace element studies are highlighting might be different from what people have thought. Yeah, and so the implications for the geodynamics, this is a very simplistic argument, but hopefully it can raise discussion. So you have two ways to transport materials from the lower crust into the mantle. You have these short wavelength drips, Rayleigh-Taylor instabilities, and longer wavelength peels or delaminations. And my geophysics colleagues tell me that a prerequisite for delamination is that you need a weak point or a weak layer to have this separation. So that's fine where you have the jelly sandwich type model for a felsic crust and an ultramafic lithosphere underneath. But a more mafic crust with an ultramafic lithosphere does not have such a pronounced weak layer. So it may render the idea of delaminations less likely. You might say in the inverse, are drips more likely? Obviously, there's smarter people than me on this call who would know about that, but these are points of future study, I think. And okay, so the final implication, the final conclusion is actually quite nice. So if you look at Archean continents being more mafic than previously expected, they would have higher density, and isostatically they would have a lower elevation. They would be thinner, and they would sit lower in terms of their isostatic equilibrium. And then we calculated the difference between a felsic Archean continent and a mafic Archean continent, and there'll be a difference significant, about 2.2 kilometers relative to these two different compositions. Now, if you then put that into a very simplistic box model for ocean volume, you work out with an Archean continent that you would have submarine continental surfaces. There will be an ocean above, it's about 1.3 kilometers in depth. And this then ties into ideas about continental emergence. People have modeled this, Flamel 2008 in EPSL. Maybe you didn't have as much continents above the surface in the Archean as you might previously have expected because of this compositional variation. Also has implications for the emergence of life. So two of the competing models for the emergence of life are these warm, wet ponds that were subaerial, as opposed to these submarine hydrothermal vent environments. And I think hydrothermal vent environments were probably popular way back, and I think warm, wet ponds are becoming more popular nowadays. But you have to ask the question, if you don't have a lot of land that's subaerially exposed in the Archean because of this hitherto uncertain compositional variation, does this throw a spanner in the works for arguments that rely on a lot of subaerial exposure? And I've highlighted a paper here in Nature Geoscience from 2 years ago, I think, Boswell and Wing, Johnson and Wing, not Boswell. Boswell's the first name. And they use isotopic data to show that actually the Archean continents were mostly submerged, which is kind of nice because it corroborates the conclusions that we've drawn from this petrological argument. So here, I'll just leave this up as a conclusion screen. It's nothing that I haven't said already, and perhaps I've run slightly late. I do apologize, Luke, but perhaps it's time for some questions now.